So continuing where we left off, let's take a look at how we can address the challenges in a bit more detail. So in the pre-training stages, the data and the compute are the two biggest challenges. In fact, the data itself has multiple facets to it. So the first challenge that exists with data is you might have low quality or noisy data, and this comes from because you're going to entirely depend on the web for this level of massive amount of data that you need for pre-training to be successful. It can't just be local documents that you have locally. So that kind of a large scale web data set that you're collecting is bound to have low quality data, it's bound to have noisy data, duplicates data, etc. So how do you deal with being able to take that data set and cleaning it up? Because if you don't do it correctly, there is a significant chance that the model is learning fake linkages, relationships. It's also learning toxicity, it's also learning biases that are potentially there, it's hallucinating facts which are not real, etc., etc. So to mitigate, obviously you need big data principles for massaging, processing, but you also need aggressive data cleaning ability, deduplication ability, filtering. You've got to have quality checks at large scale be deployed, and a lot of it has to be grounded in human verifiable labels. So that's why it's a enormous task to get good quality data for LLM pre-training. The second angle to data is there could be biases and toxicity which is embedded in the data, and if you just feed that as it is, you're going to worsen the problem of the bias becoming a significant decision variable, or bias becoming inherent in your model. So you've got to really watch out for what kind of ethical risks you are putting into the model as a result of such biased data sets. It can create reputational harm for your company, and all it usually takes in this age of social media is just one or two instances which are dramatic and which are uh, you know unwittingly viral. So how do you mitigate? There is no magic answer. You've got to incorporate bias detection from the beginning. A lot of it is dependent on human generated variables again. And in fact, one common pattern that you'll see here is human feedback loop is extremely important for good quality data. And in fact, there are standalone companies like Scale.ai, which built their entire business model around generating such data sets with such guarantees. So anyway, coming back, incorporating bias detection at the data sourcing pipeline itself, toxicity filtering during selection of the data, all of that plays a critical role. The third problem that exists is data imbalance. Again, super common. The reason being, most of the wild data meaning data that's present in the World Wide Web without curation, is English language, right? And it predominantly catered to a English speaking audience, but that originated, that has cultural underpinnings, that has the local flavor, the local masala of the American geographic region. So what's resulted is, from that is, the World Wide Web is predominantly uh, older data sets which have been, uh, which have a strong leaning towards American English contexts. And if you look at social media, on the other hand, the data for which is not indexed and available for LLMs to get pre-trained on, most of social media usage happens wherever the largest populations are. And if you look at that for context, that's just the Southeast Asia region along with China, which accounts for half the population in the world. So as a result, you've got this corpus of data sitting for pre-training, not really directly contributing to the language in which this, or languages I should say, with which this entire half of the population is natively communicating. So naturally, there's bound to be friction. Now, in your models, if you've used such overrepresented data or underrepresented data, it will manifest in many ways, right? It will manifest as the model not being good at certain types of biases, right? We spoke a bit about the example with pronouns, right? Being able to generalize from underrepresented data that um, women in the medical field are not doctors, but they are nurses, is actually the wrong kind of stereotype to propagate, right? There is no reason, there is no inherent reason for that kind of a, that kind of an eventuality. But it's just that the data set itself is biased when you fed it in. So that comes from underrepresentation of certain populations, overrepresentation of other populations. So if you don't do it, if you don't do the curation of a balanced mix of this, right, across domains, across sensitive variables, across languages, across culture, at the data assembly stage for pre-training, you run into this big risk in a big way. The other problem that exists is also whatever is predicted as the next token, and therefore the responses that LLMs come up with in well-known contexts, when you start to do zero-shot applications or few-shot applications in other contexts which are not represented well in the data sets, it might come up with um, wrong answers, and it might come up with hallucinations, which are even more dangerous to detect. So this is a significant problem, data imbalance. A fourth problem that exists is leakage of sensitive information from the underlying data. The most classic example of this would be um, you go look up the World Wide Web, and somebody somewhere, let's say uh, some government system, has provided their entire national identity database, indexed it on the web for some reason, and as a result, everybody's records are available. That's a very nasty security issue, right? Uh, Generalizing from there, you've got, let's say, code repositories, right, which are having samples of people's ID cards or people's phone numbers, email addresses. Why? Because somebody used it for testing, and that's available now as a test file in that repository in GitHub, and the LLM has gone and trained on that, and so all of those mobile numbers are now visible. So these are all very common occurrences, because when the datasets were generated at that time, we never thought that beyond the search engines, these datasets will ever get exposed through publicly accessible interfaces like chatting interfaces, right? But now the world has changed, but the datasets have remained from decades ago, uh, years ago as well. So significant issues with respect to sensitive information, copyrighted information being leaked out, um, and as a result, it can result in intellectual property lawsuits, private data being leaked, resulting in big fines, especially in the era of GDPR and DPDP, etc. So, how do you mitigate? At the point of data's processing itself, you use PII scrubbing tools, which removes this information. Um, you choose your data sources in a way that's careful, right? In fact, most of the common answer to um, these problem statements is the choice of trustworthy, high quality curated data sources itself, right at the source. Okay, the fifth problem is outdated or stale data. We spoke about that briefly. So how do you keep the foundation model itself continuously up to date with newer data? You can't do it on a weekly basis, obviously. Pre-training itself takes weeks. So old web snapshots are typically watermarked when LLM gets released. So the ability for anybody to use that for time sensitive tasks becomes lesser. So you can't use, for instance, GPT-2 and ask them who won the US presidential elections in 2024, right, or 2025. That's It's not something that it's geared up to answer. So how do you regularly refresh datasets in a way that's not too expensive? Um, that's where RAG technique come into play, but we'll take a look at it later with some examples. The last problem that's possible, the challenge I should say, is that there are engineering challenges to solve, right? If you've got all the data sorted out, sourcing, quality, bias, etc., uh, at the end of the day, now you've got all the data related, sourcing related challenges sorted out, but then you've got all this mass of data available to you. What can you do with respect to speeding up the pipeline? So at large scale, it's a huge bottleneck. In fact, that's the biggest time sink for the entire pre-training stage, which is data processing. And then going over this data multiple times, because LLMs don't just have one iterations, right? Um, so in fact, in many cases, if you've got pipelines to read the data from various sources, those pipelines are fundamentally dependent on network, right? And network latencies are the slowest compared to anything else in terms of the computer hardware, right? Memory is the fastest, CPUs, like CPU and memory go hand in hand. Disks are slower, network is way slower. So if you've got all this data coming over the network, which is the, let's say, the wide area network, public LAN kind of a network, that's super slow, right? That's going to be the biggest bottleneck. So then that's why most of these companies end up having, the ones who are building these large foundation models end up having dedicated networks. And even with that, the ingress is a significant challenge, right? For all this data to come in. So it slows down the training cycles. Even if the compute is available, the GPU cluster is lying idle and the data is still being collected in the first place. So you've got to use big data engineering techniques. You've got to use, at times, even synthetic data to get to the problem statement that you want. But you'll have to be cautious about it. Synthetic data is not the answer for everything. But for certain problem statements, for certain types of LLMs that you're building, it could be a big boost. Like for instance, if you use deep learning techniques like GANs, right, to generate synthetic data that meet certain requirements, that might actually be more useful or faster to build, like let's say, distilled models or quantized models, than trying to source the entire data set of a very large sample set to yourself, large sample size yourself. Okay, so that's with respect to data. Let's take a look at the challenges with respect to compute. Now, we all know GPUs, etc., but let's actually talk about other types of resources, right? Other resources which are in that compute bottleneck. Memory is a big bottleneck. So the model and batch sizes, obviously the model size is large, we spoke about it, but even the batch size for each iteration for learning can be large, right? And when it is large, that it doesn't fit in memory of a single GPU, then it can quickly result in a cluster of GPUs being worked to the same extent, right? Um, and then the moment you have a distributed setup, you have problems of out of memory issues because um, latency manifests as failures, right? So you're expecting an operation to finish across multiple, multiple processing units across multiple machines, and if one of the processing units takes a bit longer, then it manifests as a failure. The failure manifests as, let's say, out of memory because the data set does not exist, so the reference does not exist, etc. So frequent out of memory errors is the reality when you do large scale pre-training, even for deep learning, definitely for LLM pre-training as well. So you've got to be really methodical about uh, you know checkpointing progress, right? So that you're not wasting valuable cycles, because you don't want to do like weeks and weeks of effort and then hit a out of memory and then start the process all over again from the beginning. That would be wasteful. The other mechanisms that exist for mitigation is to use uh, compressed representations of floating points. So don't use the regular 32-bit kind of a floating point representation, because that's very precise, obviously. But in most cases, for pre-training kind of exercises, anyway, the learning itself is inherently capable of handling noise. So reduce the precision to 16-bit and then use it. Obviously, when the final answer wants to get computed, or for the fine tuning layers, right, for the final layers, you might want to use the full precision that you have access to. Obviously, model parallelism is also very important, not just data parallelism, but also model parallelism. Checkpointing and failure recovery is a very critical challenge, right? So without proper checkpointing, that failure can result in significant progress loss. So then you will have to compute all over again from the beginning. So retraining becomes an issue. So save frequently, but also save in a way that you can resume from those checkpoints. And this should also be coupled with the storage infrastructure, right? Because checkpoints need to be on persistent storage, which is reliable, so that even if the nodes restart for some reason or network accesses get disrupted, you have the guarantee that the data that's persisted will be available to you, like after the rectifications are done. Um, so that is an important aspect of checkpointing. So that should also be done as part of your pipeline. Compute inefficiency, again, it's very common. The reason being the data pipelines that you write might not be optimal. So you've got GPU time, which is idle because you've written code in a way that's suboptimal. The classic example of this is in the world of big data with divide and conquer kind of approaches that Spark or MapReduce or Hadoop provides. If you do all the work in one machine, let's say for instance the driver machine, the workers are all workers in Spark are just lying idle, and you might actually do this mistake even inadvertently. You might just be executing some code and suddenly you invoke regular Python like syntax without Spark algorithms or modules. The code will still run because PySpark is very closely integrated with Python, and the code will still run, but it'll run in the driver, and it'll bring all that mass of data into the driver to run that entire thing. Firstly, that's slow. Secondly, that workers are completely wasted in terms of usage time, right? So that's inefficient. So you waste valuable compute cycles in this. So how do you mitigate? Obviously, you use the right big data principles, which is data parallelism and model parallelism. You optimize data loaders so that it's much faster. Serialization plays a critical role. You use fast I/O for various types of frequent I/O activities, like checkpointing is a good example. So one common technique is to have checkpoints happen to a SSD because it happens so frequently and it needs to be persistent. So you can keep doing it to an SSD, but then the rest of the computational and large data sets which are getting written get written to regular disk. The fourth kind of a compute bottleneck is network bandwidth. So here, the distributed nature of the cluster means that multi-node communication suffers from interconnect bottlenecks that exist. So this slows down the entire training, especially if you do iteration-based approaches where all of this mass of data gets processed and then weights get adjusted in bulk. That kind of a batch process is fundamentally dependent on the slowest executing node. You can't claim that the batch is finished unless the slowest executing node is done. So you're only as fast as the slowest node. So how do you mitigate this? You make sure that the skew is handled well, which is part of data parallelism, but you also ensure that the network issues are all sorted out. So use high bandwidth, low latency connections between the machines, and then you can use appropriate communication frameworks that make it go faster. Sensitivity to hyperparameters is a common problem. It's there for machine learning, definitely there for deep learning. Significant problem here as well. So if you use the wrong learning rates or the batch sizes, then you go through cycles of work only to realize that um, that the convergence to a specific optimal number is not there for the learning rate or the accuracy, rather for the accuracy, and so you'll have to begin again. So waste of resources. So carefully follow the best practices, like for instance scaling. Start with conservative settings and then gradually scale it up, etc. Storage bottlenecks are also possible because these are massive data sets you're writing to disk. We just spoke about it a couple of minutes ago. You might want to use a mix of hybrid storage options here, so that you're not starving GPUs while things are getting written to disk. Okay, so we'll pause here. In the next video, we'll take a look at uh, what does versioning, what does CI/CD look like for LLMs.